Okay, so we're going to do an example here on the compression member design. We're going to check the suitability of this cross-section to carry load, the applied load NED of 3,000 kilonewtons in compression. So the member being 6 meter in length, so the length is 6 meters. It's grade S275 steel, and this is the cross-section properties. Cross-section definition, sorry, it's 356 by 368 UKC 192. So it's 192 kilograms per meter. So we're going to use it for today. We're going to do the first two checks, which is local buckling check and the flexural buckling check in there. The first thing we need to do is just understand what the cross-sectional properties over there in terms of cross-sectional strength. So we have remember. Okay, so we're going to go to the blue book now. I'll show you the blue book in the next lecture. But in the blue book, we'll find from there we'll find the cross-sectional properties. Okay. So what are the cross-sectional properties that we need? So we need the overall height of the section. Okay. So we go to the blue book, we'll get the height of the section, we can look it up. We get 355.6 millimeters. We also need the width of the section. B. That width of the section B. That's 368.6 millimeters. We need the thickness of the flange. Okay, so the thickness of the flange being equal to 17.5 millimeters. We'll need the thickness of the web. Thickness of the web is equal to 10.4 millimeters. We might need the radius of gyration, or sorry, the root radius, or it's equal to 15.2. Might need the overall cross-section area in there, which is 164 centimeters squared. And what else might we need? We might need the radius of gyration about the major axis, which is 15.6 centimeters, and the radius of gyration about the minor axis, which is 9.43. As you'd expect, the radius of gyration is equal to, so we know that I is equal to the square root of the second moment of area divided by the cross-section area. So about the y-axis is the radius of second moment of area about the y-axis divided by the area, square root of all that. And we know that it's different about the y than the z, so therefore the radius of gyration about the y-axis should be bigger than the z-axis. Okay. So that's the blue book. We also know that it's we know that the steel grade. Right, so this all of this is for the section property 356 by 368 UKC 129. Okay. So 129 being the mass is equal to 129 kilograms. So every meter, this stuff that we buy is 129 kilograms. So the steel grade is S275. Okay. And then from table 3.1 within EN 1993 part 1, that will tell us that for grade S275 with the thickness of the flange less than or equal to 40 millimeters, that implies that the yield strength is equal to 275 newtons per millimeter. squared. Okay. So we go to that table. So on Monday's class, we'll go through the code and recap where we get all these from in the code. But so once we look up that table 3.1, we can find this grade 275. We know the thickness of our flange. So in this example here, thickness of the flange is equal to 17.5. It's less than 40 millimeters. So therefore, Fy is 275. If it was greater than 40 millimeters, then we'd have to reduce the Fy down as per the table. Okay. So the first thing we're going to do is we're going to is the local buckling check. And how do we do that? We do that by classification of the section. Okay, so e.g. is it class 1, 2, 3, or 4. Okay, so we need to decide which the classification of the section is going to be. Okay, so we go to the table 5.2. So this is EN 1993 part 1 in there. And so we're going to need to know what the epsilon value is, which is on the bottom here. We said that the Fy is 275. So we know that epsilon is equal to the square root of 235 over Fy, which is equal to the square root of 235 divided by 275. And so that's going to be equal to 0.92. That's the first thing. And now we're going to classify the section. So we're going to classify the web first. There's the web here, C over T ratio. Okay, so we're going to classify the web first. So we're going to classify the web. Okay, so the unstiffened height of the web here, and from the picture over there on the left-hand side, is going to be equal to the overall height of the web, overall height of the section minus twice the thickness of the flange, minus 2 times r. Okay, so in other words, the overall height of the section is the height here, with the thickness of the flange, which is up there, and we have the little radius value here in the corner, r. Okay. And so we got all these out of the blue book, so we got 355.6 minus twice the thickness of the flange, so the thickness of the flange was 17.5, minus 2 times the thickness of the radius, 15.2. When we put all that in, we get 290.2 millimeters. We know the thickness of the web, which we got straight from the book, 10.4 millimeters. So therefore, the ratio, so the slenderness of that web is unstiffened length of the web, CW, divided by the thickness of the web, which is 290.2 divided by 10.4. Which is 27.9. Okay. So it's 27.9. So for us to have a class 1 section, so if we want to have a class 1 web, then the C over T ratio has to be less than or equal to 33 epsilon. So for class 1, the C of web, or the thickness of the web, is less than or equal to 33 epsilon, which is less than or equal to 33 times 0.92. Which is less than or equal to 30.5, which it is. So our C over T ratio is 27.9. It's less than 30.5. So that implies class 1. Okay, so it's a class 1 web. If it was that C over T ratio, if that C over T ratio here, that's the limit, 30.15. If, for example, we ended up as being 31 here, and the CW over TW is 31, then we wouldn't be class 1. We'd be greater than 33 epsilon, but we'd be less than 38 epsilon, so therefore it would be a class 2 section. If it was between 38 epsilon and 42 epsilon, it'd be class 3 section. was greater than 42 epsilon, it'd be a class 4 section. We've got a class 1 web. Now we're going to do the flange, so the same table 5.2. Just the second sheet of that. We want to classify. We want to classify the flange. Is that? So we need the C over T ratio for the flange as well. We're going to classify the flange. Okay, so this the unstiffened length of the flange is going to be half the width of the flange minus half the thickness of the web minus the R value, because we've got R is in here. We've got the overall width of the section is B. So if we get half through that, then we have to take away the half of the web that's left on the other side. So DW. Okay, so we've got BOW is to get halfway in, and TW gets us to the edge of the, let's say the right hand edge of the web. Then the radius, then will get us right to the edge of the C value there. Okay, so that's where that value comes from, just straight from the geometry. And then from the blue book, we'd found out that B is 368.6, divide that by 2, minus the thickness of the web, which is 10.4 divided by 2, and minus again the root radius is 15.2, and that's going to give us a value of 163.9 millimeters. And we know that the thickness of the flange, straight from the blue book that we got all these dimensions from, that we wrote down on the first page, is 17.5. So the unstiffened width of the flange divided by the thickness of the flange is equal to 163.9 divided by 17.5, which is 9.37. So if we want a class 1 section, we're under compression, then what we need is C over T is less than or equal to 9 epsilon. Okay, so class 1, C of the flange divided by thickness of the flange has to be less than or equal to 9 epsilon. It's less than or equal to 9 times 0.92. So that's less than or equal, which we're not going to be, because that's so less than or equal to 0.8. 9 is 81, something like 8.2. So that's not true. Okay, we have no there. Okay, so for class 2, we need CF 1 over TF to be less than or equal to, for class 2, 10 epsilon in there. So we could try 10 epsilon, which is less than or equal to, and epsilon being 0.92, so 9.2. So it's not. So no. So for class 3, CF divided by TF to be less than or equal to, now on to 14 epsilon. Okay. That's CF divided by TF, which is 14 epsilon, epsilon being 0.92. That's 13.2, and that is okay. Okay, so it is class 2 or class 3. Okay, so that implies that the flange is class 3 as width of the flange divided by the thickness of the flange is less than or equal to 14 epsilon, which was equal to 13.2. So that implies, okay, that's class 3. So I'll put the web was class 1. So we take the overall section. Section is class 3. Okay, so whichever is the lowest one, or the worst case, I suppose, we take the overall section of. Yeah, Oisin, you want to ask a question?
Yeah, would you be able to just go back on the last slide for 2 seconds, just explain what it is or what the
Yep.
yeah, C for class is that in bracket 0.92, and then what's underneath it?
For class two, sorry.
Or
For
class
class
one,
two,
sorry.
so class one was no is 9 times 0.92, and then when you work that out, it's 8.2 or so. The next one is 10 times 0.92.
Oh, perfect. Yeah, yeah, that's fine. I just
And
thought
then
it
work
was I
that
thought
out.
it fit 15.
Yeah, sorry, it's just I shouldn't be trying to squash it in. So you have 14 times 0.92 for the last one, which is equal to 13.2. Yeah.
Perfect.
So I've just put in, so you see the epsilon down here at the bottom, 0.92 on the bottom of the page. I just substitute the epsilon in, and that gives us the limits. And when I go up here, I checking this R ratio, which is 9.37. So I can see that it's not less than 8.2, so it's not class 1. It's not less than 9.2, so it's not class 2. But it is less than 13.3, so it is class 3. Okay, so it's not class 2, not class 1. It is class 3. Is that right, Oisin?
Yeah, that's perfect. Nice.
Yeah, good. No, thanks for stopping me, because it's important, because if you needed to stop me, then that's probably half the class needed the same thing. So any other questions on that? Okay, so we're on, so it's a class 3 section. So we know the flange is class 3, we had the web is class 2, but we have to take the overall sections, whichever is the worst of the flange and the web. In this case, the overall section is class 3, because the flange is driving the solution. So what does that mean? So just what does class 3 mean? So it means that effectively you can get to material yield, but local buckling limits ability of the section to attain consistency. Okay, so we're going to be able to get to the yield point, but then after that we can't get any further. We can't get into the full plasticity in there. So it's a class 3 section. When we're talking about members in compression, that doesn't really change the formulas in there. So it just means that, so that implies that the cross-sectional resistance cross-section resistance for the member is going to be just the elastic resistance. The elastic resistance, which is the cross-sectional area times Fy. So if it's a class 1, class 2, or class 3 section, so that's for a class 1, 2, or 3 section. So the fact that it's class 3 doesn't really impact it. You wouldn't get a better cross-sectional resistance for class 1 or class 2 according to the design codes. So that implies NPLRD. So we have the cross-section area, which is 164 centimeters squared, multiplied by the yield strength, Fy, which is 275 newtons per millimeter squared. We can't multiply centimeters, and we've got different units there, so we better turn in the 165 into millimeters squared, so 164 centimeters squared. Turn that across into millimeters squared, so multiply by 100. That gives us millimeters squared. And then multiply by 275 newtons per millimeter squared. And from that, we should get a value out as a calculator. Calculator here. Calculator. 164. 164 Okay, so you get 4510 by 10 to the power 3 and newtons, and then turn that into kilonewtons divided by 1,000 is 4510. Okay. So that's a cross-sectional resistance. So in other words, that's how much the member could take in compression load if we don't have any global buckling. So the next thing we have to check for is global buckling. So we've checked it for local buckling, and we're not really affected by local buckling. The local buckling might happen just after yield happens, so we can use the full cross-sectional resistance as per the yield. We might have global buckling, so that's the next check we have to do. So we're going to have to check the global buckling next, or the lateral buckling. Okay, so that's the next check. So this is the second check that we're going to do, which is the lateral. The lateral, or also known as global or flexural. Lateral. Flexural buckling. Okay, so we're going to do that where we have we know what this cross-sectional resistance value is. We've just worked that out from here. That's 4510. That's 4510 kilonewtons. We know what the partial factor of safety is, so that's just 1. That's the material partial factor of safety. What we don't know, and the hardest thing to work out, and this is what is this buckling reduction factor. Okay, so that's the buckling reduction factor in there. So we need to work that out from these equations. So the first thing that we need to work out before we go through all these, we need to work out what the imperfection factor is, what the normalized slenderness value is, and once we get that, we plug in into these. So let's go on and try and do that. So we're going to go to table 6.2. So we want to work out which buckling curve that we're going to need first. So we know that the height of the section is equal to 355.6. We know that the width of the section is equal to 368.6. So we got that from the blue book. So therefore, the height to width ratio is going to be equal to 0.96. It's about 1 in there. So it's a UKC, so universal column. Usually the height and the width are about the same. So we can see that that's less than or equal to 1.2, okay, because we have this limit to check. The HB is less than or equal to 1.2. The next thing we have to do is check the flange thickness. So we know that the thickness of the flange is equal to 17.5 millimeters. And that's less than or equal to, well, it's less than or equal to 40 millimeters, definitely less than or equal to 100 millimeters. So that's where we are here. So the next thing then we have to, which of the buckling curves, YY or ZZ. So when we're using, and we have S275 steel. And so when we're using about the major axis, we're using buckling curve B, and we're using buckling curve C about the minor axis. So table 6.2 implies use buckling curve B for buckling about the YY, and use buckling curve C for about the minor axis. That's it. Okay. So then we go to table table 6.1. It will tell us that for buckling curve B, we're going to use 0.34 for the imperfection factor, and buckling curve C, it's 0.949. Okay, so for about the major axis, alpha is equal to 0.34, and for the minor axis, alpha is equal to 0.49. Okay, so that's so that we've now got the imperfection factor. So what we're going to need to do now next is work out what the normalized slenderness value is. Okay, so we're going to work out what the normalized slenderness value is next, and once we know that, then we can get what the reduction factor is. Just hold on a sec here. Okay, sorry about that. Okay, so we now have the imperfection factor that we need. So we also need to work out what the normalized inverse value is. Okay, so let's work out what the normalized inverse value is. Okay, so we said that the reference slenderness value is equal to, so the reference slenderness value is equal to 93.9 epsilon, which is 93.9 times 0.92, which is 88.4. Okay, so then so that's the reference value. So if we look around the major axis, which is around the y axis, then the slenderness value is equal to the critical length about the y-axis divided by the radius duration about the y-axis. In there, from the question, we have 6,000 millimeters is the length, and then divided by radius duration, which is 15.6 centimeters, so it's 156 millimeters. So we got that straight from the blue book, and that gives us a value of 38.3. That's the radius duration, or sorry, that's the slenderness, and then the normalized slenderness value we said is equal to the slenderness value divided by the reference value. So that's the 38.3 divided by that reference value, which is 88.4, and that's going to give us 0.433. Okay, so that's the normalized slenderness value, and we already have from the page before, from table 6.2, we've got the reduction factor alpha, or the imperfection factor, is 0.34. Okay, so we have that from the previous page. So there it is there, 0.34. Okay, so that's the major axis. If we take the minor axis, but the ZZ axis, the slenderness value again is going to be the critical buckling length about the Z axis, the radius duration about the Z, so that's 6,000 millimeters divided by, and from the blue book, it was 94.3, well, it's 9.43 centimeters and 94.3 millimeters. That gives us a slenderness value of 63.6. And the normalized slenderness value is equal to the slenderness value of the Z divided by the reference value. So 63.6 divided by 88.4. And that's 0.719. And then we know from the table, which table is again? 6.1, that's supposed to be table 6.1. Alpha we got from table 6.1 is 0.49. Okay. So then we can, so we have those two values now. We have the normalized slenderness value and we have the imperfection value. So we can work those out now. Okay, so we're going to put those into the equation. Sorry. Okay, so into a half into 1 plus alpha into normalized slenderness value of minus 0.2 plus normalized slenderness value squared. Okay, so that's the equation. So in this side of it, we're going to put it in half into 1 plus 0.34 into 0.433, which is the normalized slenderness value, minus 0.2 plus 0.433 squared. Okay, so see how that worked out. So this is the reference value is, I'll just come back up here again, sorry. This reference value here is the formula that we're given within the code. So the code has the reference value is 93.9. So it's always 93.9 epsilon. The only thing that's changing is the epsilon. We know that epsilon is equal to the square root of 235 divided by fy. That's where we got that from. Okay. So down here then at the bottom, I've got 0.633 here about the y-axis. And then we can put that in to get the reduction factor about the y-axis. So the reduction factor here, the reduction factor is this formula here. So it's equal to 1 over phi plus the square root of phi squared minus lambda bar squared, and it's lambda about the y-axis. So that's 1 over 0.633 plus, 0.633 plus the square root of 0.633 squared minus the normal ascendance value, which is 0.433 squared. And that reduction factor is 0.913. Okay, so if we just do the same on the other side, okay, we'll do the same on the other side. So that normal ascendance value is a half into 1 plus alpha on this side is 0.49 into the normalized ascendance value is 0.719 minus 0.2 plus 0.719 squared. Okay, so we're just using the same formula. Same formula here, half into 1 plus alpha, normal ascendance value minus 0.2 plus normal ascendance value squared. So half plus 1 plus alpha, normal ascendance value minus 0.2 plus normal ascendance value squared. And when I work that out, I get 0.886. And then the reduction factor about the z-axis is equal to 1 over 5 plus y squared minus square root of all that. Okay, so it's equal to 1 over phi is 0.886 plus the square root of 0.886 squared and minus 0.719 squared. So that's all under square root. Okay, the square root of, so run out of space. All that's in there. So I have 0.719 squared in there. So when I work out that, I get 0.713. So I've got the reduction factor about the y-axis is 91%, 0.91, whereas the reduction factor about the z-axis is 0.713. So this one is going to be the critical one because it's a smaller number. So the critical buckling value about the z-axis is equal to the reduction factor about the z-axis into the NPL RG divided by gamma m and naught. And so take that on to the next page. So the reduction factor above the Z or D is equal to, the buckling value is equal to the reduction factor in PL all over gamma M, factor of safety. So let's just go back and find out what the, so we have 4, 5, so the cross-sectional resistance is 4510. 713, so that's equal to 0.7713 divided by 4510, I think it was, divided by the material factor of safety, which is 1. We multiply that out. So multiply by 0.713. That gives us 3,215 or so kilonewtons. Okay, so that's the buckling. So the flexural buckling about minor axis, which is the one that's driving this one because it's a smaller one, is in P Z or D, which is 3,212 kilonewtons. Okay, so that's what the that's how much load we can put on this section. We compare that to the cross-sectional resistance. So if we could stop that lateral buckling, we could get up to 4,510 before we yield the material. But as a result of the lateral flexural buckling, like a ruler kicking out sideways as you squash it, we have only 70%, 71% of the capacity in there. So if we can stop that element from moving sideways, then we could increase its overall compression resistance. Okay, so that's the example done in there. So stop recording.